Hello everyone, thanks for joining this week's UCL Radar Group Seminar. This week is the first of a double header on our PETRAS IoT project. It may be a little off topic for the Radar Group, but has similar challenges and we can apply similar techniques to those used by this community. So this is the talk outline. I'll start with a brief description of PETRAS, although Matt's done some of that already, and the SDRIOTSS project. Then a reminder of the Aresta platform. Then I'll describe the specific IoT signals considered in this study, the processing chain developed to handle the signals, and some results from the processing that we've carried out. So PETRAS is a hub for research all things IoT in both consumer and business environments, funded by UKRI. It's led by Professor Jeremy Watson here at UCL. The purpose of the hub is to investigate issues of privacy, ethics, trust, reliability, accessibility, and security as they relate to devices, systems, and networks. PETRAS. SDRIOTSS is the project proposal we submitted to PETRAS, software-defined receiver for IoT spectrum survey. The problem we proposed investigating is what's out there. The number of IoT devices out on the street is rising rapidly. Spectrum planning and security authorities need independent assessment of the signals and protocols which exist in the environment. The real challenges, though, are the very large quantity of data involved, hence the need to pre-process the data at the edge and the need for continuous monitoring. SDRIOTSS was a short-term project which has just been completed. The final report was issued last week. At its heart, the proposal included the exploitation of our Aresta platform as a device for IoT monitoring. Using Aresta, we proposed to create a database of signals of interest, which we could then use to design and test suitable processing chains to identify the parameters of the detected waveforms. DSTL at Fort Housestead are keen to investigate IoT threats, so we're an ideal partner for this work. Sorry if you're already familiar with Aresta from our previous talks, but we think it's a really capable platform for all sorts of RF sensing. So we harp on about it every opportunity. The platform was developed under phase 1 and phase 2 of the DASA Invisible Battlespace program, covering about 18 months duration. This generation of RF SOC that we use provides direct RF sampling with ADCs operating at 4 gigs and DACs operating at 6.5 gigs. You can see the RF SOC that we use in the image here. RF SOC also includes FPGA fabric and multi-core ARM processors on the same die as the RF circuitry. The infrastructure we've built lends itself to design and implementation of a wide range of processing solutions. We have designs for FMCW radars with on-chip deramping and decimation, passive radar using Wi-Fi or DVB signals as illuminators, and radar ES with 2 gigs of instantaneous bandwidth. We also easily combine designs such that we have, for example, active radar and passive radar joint designs in which both systems can operate in parallel. So it wasn't a big stretch to translate this to IoT signals. So there are many IoT signals out there, but the 2 signals of particular interest to DSTL at Fort Housestead are LoRa and Sigfox. These 2 signals are very different, so we decided to concentrate on the LoRa protocol for this short piece of work. LoRa consists of multiple chirp signals, so very familiar to radar engineers. Each chirp represents a symbol in the message. In Europe, LoRa occupies about 9 megahertz in the 868 megahertz band. Again, also in Europe, LoRa signals can have bandwidths of 125 kilohertz or 250 kilohertz. there are other options in other parts of the world. Important factor is spreading factor, and this defines the gradient of the chirps and therefore the time taken to transmit a message and the integration available at the receiver. Coding rate is associated with payload redundancy for error correction, although this is not something we can determine just from the RF profile. Data is encoded by the start frequency of the chirp. A LoRa message is shown here in the two figures. On the left is a time domain capture, and on the right is the spectrogram form. Okay, so the LoRa protocol consists of a number of up chirps here. I'll put the drawing on. Work? No, it doesn't work. Number of up chirps here. This number is configurable in the protocol, or it can be 0. Then it's followed by 2 up chirps here, and then 2 1/4 down chirps, followed by the message payload. So our configuration of a Arrestor for LoRa capture. The left image shows a schematic of the data capture system. The green box represents Arrestor, the pink box a 5Pi device, which is an IoT communications device that we're using as our transmitter. So on the Arrestor, it consists only of one channel of the Arrestor system, an antenna and a bandpass filter, and on the 5Pi side, just an antenna and some optional attenuators just to reduce the signal to noise ratio. The important part is that GPIO signal here, which allows us to synchronize both devices, and therefore we know when the 5Pi will transmit, so we only capture relevant data. On the right is the actual hardware solution. So with the Arrestor here, GPIO signal just consisting of a wire and the 5Pi. So we wanted to create a signal database. So we have Python scripts running on both devices with the GPIO maintaining synchronization between them. This allows a large number of captures to be initiated and run automatically, and labeled data saved to disk. We've captured over 2,000 separate captures and stored these in our labeled database. We have 2 RF socks, so we did the captures with both with separate 5Pis. A wide range of parameters were exercised during the captures, and this will be very easy to extend in the future if required, either for more parameter variation or multiple captures of the same data. Okay, now on to how we process the data. All of this is done in MATLAB currently. The data captured from the RF sock is pre-decimated to about 8 megahertz of bandwidth, centered on the LoRa band. We look to identify the 2 full down chirps which exist in every LoRa transmission. If you remember this picture here, we've got those 2 down chirps. One might consider using the 2 up chirps just prior to the down chirps, but they actually carry configuration data, so don't necessarily start at the base frequency. So identifying them could be slightly more problematic. Initial stage of the algorithm is a channelizer, where we take the 8 megahertz of data and split it into a number of 500 kilohertz channels. Excuse me. And these channels are overlapped by 50% for reduced computational load later in the chain. But the 50% overlap is there to ensure that a single signal, LoRa signal, appears in a single channel. One signal could in fact appear in multiple channels, so some data fusion might be necessary between channels, but this hasn't been considered so far. Spectrograms are created from each channel as inputs to subsequent processing stages. We use a 64 sample window with 90% overlap for the FFT, and the FFT length is 256 samples. And spectrograms cover about 75 milliseconds in the time domain. The power detection here, although it's not implemented in this software chain in MATLAB, that's because we know where the signal or the signal image is in our data. So we know where to look, but in practice, this won't be known. So the power detector reduces needless processing load if no signals are present. Niall might discuss that in future seminar. Okay. Right. Following the channelization and spectrograms, we binary threshold the spectrogram and thin to create a black and white image with narrow line segments. If left without thinning, the width of the lines is quite a confuser for the processing and can result in line segments being identified across rather than along the lines. Thin image is processed by a Hof transform to detect the line segments, which are then matched to the threshold across pixels to identify the line location in the image. Parameters of the transmission are then extracted from the line details. I'll try and summarize the operation of the Hof transform next for anybody who's not familiar with that. Hof space consists of an alternative representation of the image values using r theta as the axis. R theta can be seen in the orange line case at the bottom here. So r is the distance from the origin to the closest point of a line, and theta, the angle from the x-axis to this line r. So that allows us to define a line in r theta terms. Practically, the Hof space consists of accumulators at each point in r theta space. Each valid threshold crossing in the image space, say point P in this image, is transformed into Hof space by identifying the r and theta, which represents the point on a line on which the point could lie. The problem here is the point can sit on an infinite number of lines with differing r theta. Each point maps to a sine curve in Hof space. For each line considered, a 1 is added to the accumulator in Hof space corresponding to the locations within the sine curves. For points which lie on the line, the r theta is constant, causing greater accumulation at a single point in the Hof space. This corresponds to intersections of the sine curves. Finding maximum values across the accumulators provides an indication of the lines found. The line can then be matched against the valid points in the image to find the true extent of the line. So that's really saying that the line definition is infinite, this dotted line here. So we have to match our points we found to a sub part of that line to actually define the actual location of the line. For radar ES, where the gradients of the curves of the LFM signal is totally unknown a priori, all angles have to be assessed. But in our LoRa example, the possible gradients are well defined. In fact, there are only 8 options, which means an optimization we use is to only address those lines of interest. By way of illustration, this image from Wikipedia shows 2 lines in the left-hand image, in the image space, and the equivalent Hof space representation. The 2 lines in the image space correspond to the bright spots or high accumulator values in the Hof space shown here. Okay, a few results. So the top left-hand image here is our thresholded binary spectrogram with very wide lines. We then thin it to produce the nice narrow lines, which are much easier to assess. And when that's transferred to Hof space, we end up with these bright spots. You could just about maybe see some sine curves there, but it's very difficult to see. So these points in Hof space allow us to revert back to the image space to create lines that would be infinite length, but by matching those lines to the actual threshold crossings within the image, we can determine the actual length of these lines, from which we can find the parameters of the signal. It's robust against where the signal is within the spectrogram. So these are just some shifted images where the algorithm is run and it still finds them irrespective of where in the image the lines exist. To test the algorithm against congested environments, we overlaid here 3 separate LoRa signals from our captures and just shifted them in time and space. So they made quite a mess in the spectrogram image at the top here. We thinned it, or thresholded it and thinned it as usual, and it gets quite messy. And in Hof space, we can find 3 clusters which represents the 3 separate signals that we are detecting within the Hof space. When transformed back to image space, we find all 6 occurrences of the down chirps, although one of the 250 kilohertz chirps here is short, although it still crosses the threshold for being detected as a 250 kilohertz signal. And then we tested the algorithm against varying SNR conditions. And in this case, the signal capture is artificially degraded with various levels of noise. In this case, the signal to noise ratio is -10 dBs, so no sign of the signal within the time domain. In the spectrogram, we can still see the chirps, and the algorithm does a good job of identifying them as the actual signals in question. However, it does fall apart at around 12 or 13 dB, -dB in this case. We can still see the signal in the spectrogram and just vaguely see it in the thresholded binary spectrogram. But once it's thinned, then it's virtually impossible to see, and all sorts of incorrect lines are detected within the signal. Okay, just to summarize, the Arista platform has been configured for IoT data capture. Unattended acquisition of multiple 5-pi generated signals has been carried out, and a database of LoRa signals covering a wide range of protocol parameters has been made. Processing chain has been developed to identify LoRa signal characteristics, which is working quite well. And for part 2, what we'll be talking about is implementing the processing chain on the Arista platform using some FPGA fabric components, some ARM software components, and some Neon single instruction multi-data coprocessor components as well. Okay, that's all I've got to say. So any questions?